So that's right. Okay, so that's just an integration by parts. I know it's not the thrust of this class, but you do have to know it to be able to solve some of these integrals, so it's worth at least doing the ones that you need to do. Okay, so any questions about that? That's how we did p of x is less than a. Okay, well, let's look at p of y is less than b. It's very much the same, but this time it's going to be even easier. Well, factoring this thing out again, this time we'll be taking 0 to infinity, 0 to b of e to the negative y times 0 to infinity of x e to the negative x dx dy. Okay, and now you should have already computed the inner integral, but it turns out to be just 1, too. If you plug in infinity and 0, you'll see that it's just 1. Okay, and now we're just integrating from 0 to b of e to the negative y. That's just the CDF of an exponential. So what do we get for that?
1 minus e to the negative 1?
Yeah, right. E to the negative b. But yeah.
Or b.
Right. Okay, so now you can see inside here. This is just the CDF of expo 1. So that's all we need to do. Or you could just do the integral. The integral of e to the negative x is e to the negative x. And you plug in those things, you'll get that. All right. Well, I think we've done a lot of those, but there's one more that's worth doing, and that's the probability that x is less than y. Okay. Probability that x is less than y. What's our strategy here? This may strike you as kind of odd at first, but if you think of x and y as being two components of the same draw, we're interested in the probability that once we've done this one bivariate draw, the first element is less than the second. So that may be a little nebulous right now, but maybe it'll be a little clearer if we write it out in integration form. So we want to do an integral. And this time, how will we integrate? We have to be very careful, because this time, order is going to matter. We can't do it either way. Which thing do we want in the outer integral?
Y.
Y. Y. Sorry. It would be great if there was a better letter than Y. But go ahead. So why?
Because x depends on y, so
Right.
when you take that integral, you're going to get a new dependence on y, which you have to integrate over.
Yep, that's right. Okay, so we can put Y up here. We actually could have done it the other way too, but then we'd have to be very careful with the dependency. Okay, so let's see. So on the outer integral, you're saying we're going to put Y here and X here. So let's think about then. So what should the bounds be for Y?
The same as before, 0 to infinity.
Yep. Okay. And then what should the bounds be for X?
From 0 to y.
From 0 to Y, right. Okay. Does everyone see why you need to, if you're going to do it, why you need to have them in this order? What's going on here is the bounds of this integral involve one of the variables. So if that happened in the outer integral, that would be bad, because that would mean that the answer, instead of being a number, would involve the variables, which would be bad. So we want the only dependency to be in the inner integral. That way, when we do the outer integral, that variable gets integrated out. We end up with a number instead of with something that depends on x and y. Okay. X e to the negative x plus y dx dy. Okay, so now we've got to integrate. Oh, I actually did it in reverse. Dy dx.
It's dx.
Oh,
dy.
was it the xdy? Okay, thank you. There we go. All right. So now we need to integrate the inside thing from 0 to y. Oops, sorry. Yeah. 0 to infinity of the integral of the inside thing. Well, let's pull out the e to the negative y. That should be easy enough to handle with. Oh, another one of those. 0 to y of x e to the negative x dx dy. This piece, well, we should have evaluated before. What do you get for the inner piece?
1 minus y plus 1 e to the minus y.
Oh, one more time? That sounds right, but go ahead.
1 minus y plus 1 e to the minus
Okay.
y.
1 minus y plus 1 e to the minus y. Okay. And what's another way to look at that is that over here we computed this was just the CDF of the thing with this distribution, and we already evaluated that over here. So now all we're doing is exchanging y where a was before, and it's the same integral that we already evaluated. So we don't need to evaluate it again. That's just a trick, though. Okay, and now we have e to the negative y times this and times this stuff. Okay, well, now what do we do? Now we've got to integrate this from 0 to infinity. So I'll leave out the integral. So first, let's break it into pieces. 0 to infinity of e to the negative y minus y plus 1 e to the negative 2y dy. Okay. Let's evaluate each component of this. First component, we're just integrating e to the negative y from 0 to infinity. What do we get there?
1.
1, right. Exponential PDF, it's a 1. What do we get in this part? Well, that part's going to be kind of annoying to do. But here, I'll put what the answer ends up being a half. Okay, so you can verify that for yourself. I want to make sure we get to the next couple of these so that there'll be at least some more tools for the homework. But you'll end up getting 1 minus a half, and then final answer is a half. Okay, let's do some sanity checks. A half is between 0 and 1, that's good. A half is a number. This should be a number, right? As opposed to something that depends on x or y. Depends on x or y, you're in trouble. Probability of x is less than y should just be a number. Okay, so the answer looks like it makes sense. And you can evaluate it for yourself. You should end up getting a half there. All right, so that's that one. And let's see. So, well, why don't we skip the next part of this one where we have a new density, and just move to the one about the bivariate uniform with Bob and Carla. Pardon me? Oh, I know it's a weird strategy, but I don't think we got to it in this section. But Bob was in the homework, was in my handout last week. He had an estimator, and you need to find out whether his estimator was unbiased or not. Well, since it turned out in one case that it wasn't, then he got a Dave. So, and that was Carla, and that's how we get to this week's handout. Yeah. So,
The saga.
Right. Okay. So does everyone understand the question? Okay. Someone want to propose a strategy? Yes.
So we're going to say that Bob arrives at some time,
Okay.
uniformly distributed.
Okay, so let's put out the times. Okay, so let's have time Bob, uniform, 0, 1. Okay. Time Carla, uniform.
0, 1.
Actually, let's not say 0, 1. 0, comma what?
60.
60, okay, good. Okay, 'cause now it's in minutes, so it's a number of minutes. Okay, and time Carla is also on 0.60. Okay, now what do we do? Let's get to you a couple points. Go ahead.
That x is less than y plus 5.
Okay, but it could actually, that's part of the probability.
But since it's symmetric, we'll just use 2 times that, because one could arrive first or the other.
I'm gonna have to think about it. There might, the principle of symmetry, x is less than y plus 5. Okay, okay, that might be true, but
I think I'm okay.
yeah, I think it,
It has to be, right?
Is that-
Plus p of y is less than x plus 5.
well, first, right, okay. Yeah, first, I'm gonna have to think, I'm pretty sure the symmetry holds, but he was suggesting that we take twice this. But I assume, right? But I'm pretty sure the symmetry holds, but since I'm not 100%, I don't want to write it like this. We're gonna do it another way anyway. Oh, not intersection. Right, union. Hold on here. No, actually we do want an intersection, right? We would like that,
Yeah, they're both within 5 minutes.
right, they're both within 5 minutes of each other. Good thinking. Okay. Okay, so how do we get that probability now? Well, there's one bad idea, and then there's a better idea. What's the bad idea?
Double it?
Right, okay. So when you're dealing with uniforms, we're going to go back to one of the toolbox techniques, or the toolbox techniques, is to draw a picture, okay? Because uniforms are nice. You can draw a picture. But if you have something that's non-uniform, then you have to worry about the values of the densities and things. It's not as easy to draw a picture. But in the case of a uniform, it's nice to draw a picture. The bad idea would be to double integrate and set up something like this. We'd have to worry about the boundaries and exactly where we were integrating from, because we know that, for instance, it's not totally straightforward, because if someone arrived at 7:59, then there are fewer opportunities for the other person to arrive within 5 minutes than if they arrive at 7:30. Then there are 10 minutes that Carla could arrive, for instance. So here I'm going to suggest drawing a picture. Now, how do we go about drawing a picture? Well, we start with, well, I'll give it away. We start with a square. Okay. And now we want to draw the areas where this condition holds. And then we're just going to use the fact that for a bivariate uniform, all we need to do is compute the area of the region that we care about. Yeah?
Wait, are those the same?
Okay, let me put the axes.
Oh, no, I don't
Oh,
mean
oh, sorry.
X is less than
Y is less than
X
X
plus
plus 5.
X is less than y plus 5, and x is, oh, excuse me. Thank you. Right. Of course, what I meant here was y is less than x point 5, right?
Where x is TB and y is TC.
Oh, excuse me again, thank you. That's right, okay, yeah.
Yeah.
Here, I'll put it in, but think for a second about how you would draw the picture. Good. Oh, hold this here. Oh, there we go. PC, less than TB. Okay. And now the picture, I was going to suggest putting T Carla on one axis, T Bob on one axis, and it goes from 0 to 60 here, 0 to 60 here. Okay. The goal is to draw the probability in this square. Yes. Go ahead.
Is it like a diagonal strip?
Right. It's a ribbon, diagonal ribbon. And okay. So is this what you had in mind? Okay. Was that what you had in mind? Okay. Okay. And now, before we finish drawing the ribbon, you need to tell me a few things. This point, this point, this point, and this point. Okay. What are those points?
They're all at like 5, so like 0, 5.
Right. Right. Okay. This is 5. This is 5. This is 55. This is 55. Okay. So now, what is the area we care about? Is it this, or is it the area inside the ribbon?
Well, it's 1 minus the area of the triangles.
Okay, that's how we're going to compute it. But right now, I just want to shade it. You're getting ahead of the game.